Peter Norman is an elite-level touch football athlete playing in the midfield position. As a midfielder, his role requires high levels of fitness and consistency, along with high-intensity bursts of sprinting and sudden changes of direction. The interplay of systems is fundamental in such performances, as the demands throughout the game differ, necessitating explosivity, endurance, and recovery. Peter's performance relies on the dynamic interplay where each system works in unity with one another, although at times one may be more dominant than the other. As a midfielder, Norman works at high intensity for short durations, usually engaging in repeated sprints, dynamic ball distribution, and other rapid lateral movements. As a single possession may last anywhere from 20 to 45 seconds, focusing on the adenosine triphosphate creatine phosphate, or ATP-CP system. This system relies on the ATP molecule, made up of adenine, ribose, and 3-phosphate groups, but Peter primarily uses the anaerobic energy systems before requiring active recovery. Norman's total time on field is 13 minutes and 41 seconds, meaning he's actively engaged for 34.2% of the total game, 2 20-minute halves. This indicates that he spends majority of his time, 65.8%, recovering off-field, really emphasizing the high-intensity role of the midfielder, which necessitates many substitutions for prime performance. Within his rests, you can sometimes see him walking up and back along the sideline, engaging in light movements to assist lactate clearance. This is a form of active recovery that helps maintain circulation. His work-to-rest ratio is approximately 1 to 2.14, with an average time on per interval of 1 minute and 22 seconds, and an average recovery time of 2 minutes and 55 seconds. This further proves how short bursts of high-intensity effort require sufficient recovery to sustain such a playstyle. At the beginning of the game, oxygen demand and supply are matched as Norman's aerobic system efficiently meets his energy needs. However, as soon as he engages in high-intensity efforts such as explosive sprints and lateral movements within the first 10 seconds, his body immediately relies on ATP stored in the skeletal muscles, approximately 3 times 10 to the 21 molecules. This stored ATP provides an instant energy source for short bursts of movement, but is depleted within 1 to 2 seconds. To sustain his intensity, Norman transitions to an anaerobic energy systems, first utilizing the ATP-CP system, which rapidly regenerates ATP using creatine phosphate before anaerobic glycolysis becomes the dominant energy provider. The deficit occurs because the body cannot immediately deliver enough oxygen to the muscles during high-intensity efforts, forcing anaerobic energy systems to shortly dominate until steady amounts of oxygen can be gained. Within his cells, water, or H2O, comes into contact with ATP in a reaction called hydrolysis, breaking it down into adenosine diphosphate, ADP, and releasing energy to fuel his movements. This seamless transition between energy systems is important to Norman to maintain his high-intensity performance during the early phases of play. As ATP is rapidly hydrolysized, it is quickly depleted due to constant energy demand in which the system cannot keep up with. As cells cannot store large amounts of ATP, therefore promoting anaerobic glycolysis as the predominant energy system, breaking down glycogen to generate ATP. During this process, glycogen is converted into glucose and further into pyruvic acid, which in the absence of oxygen, pyruvic acid is converted to lactate, releasing hydrogen ions as byproducts. For instance, in the second half of 43 minutes and 10 seconds to 45 minutes and 6 seconds, Norman withstands a continued effort demonstrating the reliance on glycogen breakdown to generate ATP. This process produces lactate along with hydrogen ions as byproducts which accumulate in the muscles before relocating into the bloodstream. When blood lactate concentration reaches 4 millimoles per liter, Norman experiences the onset of blood lactate accumulation, OBLA, causing increased acidity and muscle fatigue. This high-intensity sequence, plus a touchdown at 35 minutes and 45 seconds, showcases the need for rapid energy resynthesis between efforts. As a result, Norman's performance declines, forcing him to sub off for recovery before re-entering play. During Norman's off-field recovery time, such as his 2-minute 11-second break in the first quarter, excess post-exercise oxygen consumption, or EPOC, is elevated, working to return his body to pre-exercise levels. These structured rotations are very important in enabling ATP-CP resynthesis, lactate oxidation, and oxygen replenishment. Given the high-intensity role where repeated sprints and lateral movements continue to deplete Norman's ATP stores, recovery periods allow for some restoration before re-entering the game. After 2 minutes and 11 seconds of rest, approximately 90% of his ATP-CP stores are replenished, enabling him to resume a near maximal intensity. His VO2 levels remain elevated, assisting in lactate clearance by relocating lactate to the mitochondria where it is converted into pyruvate and further metabolized for energy. Matt Prowse is a high-level touch football player playing in the wing position that demands high endurance and rapid changes between jogging and sprinting. While the midfielder role has much lateral movements and constant sprinting in the guts of the play, the winger, such as Prowse, must operate more on the outside, with higher distances reaching high-speed sprints whilst also assisting in both defensive and attacking phases. This positional difference means that while both players utilise all three energy systems, Prowse's game involves a greater dominance of the aerobic system. Due to the persistent running on submaximal intensity, which is a regular characteristic in the winger position, the dominant system is the aerobic system. The aerobic system is responsible for oxidative phosphorylation, where glucose, fats, and sometimes proteins are broken down under the presence of oxygen to create ATP. This is far more efficient than anaerobic energy production, producing anywhere from 36 to 38 molecules of ATP from 1 molecule of glucose, as opposed to a mere 2 molecules of ATP from anaerobic glycolysis. As a result, Prowse's movements down the sideline are supported primarily by the oxidation of glycogen and fats. However, unlike Norman, Prowse experiences periods of lower intensity, particularly when the ball is on the other side of the field. During these moments, he is often seen lightly jogging up and back, maintaining positioning while conserving energy. This allows him to rely even more heavily on the aerobic system. Because jogging requires a lower ATP usage rate, his body can primarily metabolize glycogen and fats with oxygen, delaying ATP depletion along with reducing lactate accumulation. Even with varied patterns of movement, both players are subject to onset of blood lactate accumulation, OBLA, with high-intensity bursts. Since wingers tend to engage in more continued running as opposed to stop-start lateral actions, Prowse is likely to develop a reduced rate of lactate buildup compared to Norman. This means while Norman must be taken off the field frequently to eliminate metabolic waste products and replenish energy reserves, Prowse can stay on the field longer as his aerobic system helps sustain his energy levels for extended periods. During off-field recovery, Prowse, like Norman, is affected by elevated post-exercise oxygen consumption, EPOC, allowing lactate clearance and resynthesis of ATP. His reduced defensive contribution may, however, lead to less blood lactate accumulation, reducing the intensity of his off-field recovery needs compared to Norman, whose increased involvement in congested midfield play results in greater lactate storage and muscular fatigue. This difference between Norman's stop-start explosive midfield play and Prowse's end-to-end sprinting role highlights how different positional demands influence energy systems, lactate accumulation, and recovery requirements. To analyse my performance in the Year 12 touch football game, I reviewed my game footage and heart rate data to evaluate the energy system usage. This analysis compares my performance as a midfielder where I played for 3 quarters and a winger where I played for the final quarter. Playing as a midfielder required many sprint efforts, lateral movements, and defensive positioning. My 40 sprint efforts, each lasting between 1 and 3 seconds, were primarily attributed to the ATP-CP system, which was quickly used up. As a result, my primary energy system throughout the game was the lactic acid system, which provided energy for the high-intensity movements lasting between 5 and 30 seconds. The trade-off being the accumulation of lactate and hydrogen ions leading to muscular fatigue and a gradual decline in intensity. My high heart rate further indicates the reliance on anaerobic glycolysis as my body works to clear metabolic byproducts. While my 5 recorded instances of walking/resting allowed for brief recovery, the overall intensity of the midfield role meant that my aerobic system played a minor role. My work rate was reflected in the game statistics with 9 passes, 11 roll balls, 1 assist, and 2 tries, showing active engagement in both playmaking and attack. Defensively, I recorded 18 defensive touches, demonstrating high involvement in stopping opposition attacks, which further contributed to the increased dependence on the anaerobic system. As fatigue set in, particularly in the third quarter, I noticed a slight decrease in movement sharpness due to my prolonged time in the red zone and just being on the field after playing the whole second quarter. Compared to the elite midfielders who maintain a high work-to-rest ratio around the 1 to 2 range, mine was much worse, coming in at 1 to 3. This shows that I had significantly less off-field time recovering, resulting in a decline in performance efficiency further shown by the heart rate monitor. In contrast, my time playing on the wing in the final quarter required less overall involvement, with many more walking and jogging phases and fewer sprints. The aerobic system played a much larger role as I recorded only 9 jogging efforts lasting between 4 and 12 seconds and extended walking/resting periods, with my longest rest being 80 seconds. This is reflected in my lower average heart rate of 82% and a significantly reduced in the time in the red zone, 16% compared to the demands of playing in the midfield. Despite the lower workload, I still made 6 sprint efforts, each lasting 2 to 4 seconds, which relied on the ATP-CP system for short bursts of acceleration. Unlike in the midfield, these efforts were far less frequent, reducing overall CP depletion and allowing for fast recovery between bursts. My game statistics as a winger further highlight the lower workload with 2 passes, 2 roll balls, and 3 defensive touches, compared to a significantly higher number in the midfield. Less involvement in the game correlate with my lower heart rate and reduced time in the red zone, meaning I was able to recover more efficiently. While the reduced physical demands demands of playing in the wing meant I had more energy for sharp sprints first. My overall contribution to the team play was lower than the midfield. Comparing my performances in the two positions highlight key differences in energy system usage, workload, and physiological demands. As a midfielder, I relied heavily on the ATP-CP and anaerobic glycolysis system, leading to a higher heart rate and greater fatigue and longer recovery times. In contrast, playing on the wing position involved more aerobic recovery, reducing overall heart rate strain and enabling faster sprint recovery. The impact on the performance was clear. In midfield, I was far more involved in the play, both offensively and defensively, but at the cost of a higher fatigue, while on the wing, I had greater energy availability for sprint bursts due to a lower workload.